Hello and welcome to this new lecture of Math-S400, Mathematics and Economic Modeling. In this lecture we're going to see and prove the intermediate value theorem, which is an important result and used a lot in economics. So for the intermediate value theorem we start with a function f, and the domain of the function is just a subset of R. Okay, and in particular we're going to take this to be an closed interval. Okay, so goes the interval AB, which is closed on both sides, okay, and the function is going to take values in R. So if we draw this, we have a number A, we have a number B, so the domain is AB, and then we have a function f that takes elements in R, and we're going to assume that this function f is continuous. Okay, so for example, that's our function f. Okay, so it takes a value at A, it takes a value at B, and is continuous. Okay, so because this function is continuous, we know it has a maximum and a minimum on the domain. Okay, by the extreme value theorem, the domain is compact, right? It's closed and a bounded subset of R, so we know that f has a max and minimum on its domain AB. Okay, so if you look at this picture here, then the maximum of f will be reached somewhere at this point. Okay, so this will be my maximum value that it can take, and then the minimum will be reached, eyeballing it, it will be somewhere over here. So no, I think A is even smaller, right? So this will be the minimum here. So here f min will be reached at A, and f max will be reached at this point here. So what does the intermediate value theorem tell you? Well, if you take f min was the minimum over all elements in the domain of fx, okay, and we can take the maximum of fx over all x in AB, and then the intermediate value theorem tells you that for any value between these two numbers, okay, so let's call this, for example, C, it should be able to find a value between A and B such that f of this value is equal to C. Okay, so in other words, at least at some point this line here should cross the function f. Okay, so here actually this happens at 3 points, this and this point. Okay, but in general there should be at least 1 point. There can be more than one, but at least there should be 1 point. Okay, so that's the intermediate value theorem. So let me state it a bit more formally. So we have a continuous function f from AB to R, continuous. Then we define f min to be equal to the minimum over all x in the interval AB of f of x, and we define f max to be the maximum function value over all x in AB. Okay, so this is similar to here. So then you know that for all C in the interval f min f max, there should exist a number x in the interval AB such that f of x is equal to C. Okay, so here these 3 points are all possible values of this x here, but at least there should exist one. So we're going to prove this theorem, and in order to understand how the proof goes, let's draw a picture. So let's say that we have the interval a, b, and then you have a continuous function, something like this. Okay, so now here we have the minimum. The minimum and the maximum will be reached at b, somewhere over here. Okay, so this is the point at which the minimum is reached, and this b here is the point at which the maximum is reached. And now we take a value, let's say c is equal to this value, and basically we're trying to show that at least at some point this line here intersects this function. And what we want to do is we want to find this point. Okay, so how are we going to do this? How is this going to proceed? Well, we're going to take this interval here between this point and this point. Okay, so let me call this x1 and y1, and we're going to divide it in two. Okay, so eyeballing it, it should be probably be here. And then we're going to compare the function value at this point with the c here. Okay, so in this case, at this point, our function value is below c. So what are we going to do? We're going to say, okay, I'm going to call this x2. And then I'm going to call y1 equal to y2. So what's the idea of the algorithm? So at the starting point, I know that x1, the function value of x1, which is this one, is below c, and c is below the function value of y1. Okay. Then I split the interval in two. And here I see that the function value is still below c. Okay, so instead of x1, I can replace this by x2. And y2 here will be still have a function value above c. Okay, so x1 and y1 had the property that the function value of x1 was below c, the function value of y1 was above c. x2 and y2 will have the same property. x2, the function value will be below c, and y2, the function value will be above c. But the size of the distance between the two is cut in two. Okay. Then the next step, what can we do? We can take this as a starting point and do the same thing. Right? So for example, this now will be the midpoint between these two. And in this case, we see that the function value at this point is greater or equal to the c, the target that we would like to reach. So we're going to say, okay, this is now our new upper bound. So we're going to call this y3. And then this x2 will be, the lower bound will again be equal to the x3. Okay. So the new interval still satisfies that the function value of the x is below c and the function value of the y is above c. And then again, we can cut our interval in half. Let me use blue pen for this. So for example, here we see here at this point the function value is below our target c. So we're going to call this our new lower bound, which is x4. And then y3 is going to be equal to y4. Okay, so basically we're going to approximate this c here from below and from above by using lower bounds and upper bounds, and but each time the interval is going to be cut in two, right? So we see in the first interval had this size, the second interval was the green one, has this size, the third interval will have this size. So each time, each iteration of this algorithm will get the x and the y closer and closer together. So we hope that in the limit, if you do this over and over and over again, then this interval will collapse to a single point, and actually it will collapse to exactly this value for which the function value is equal to c. Okay, so this is the idea behind the proof. Okay, so f min is the minimum of fx. Okay, so we know that there exists in x, in AB such that f of x, let me call this x1, right? This is going to be our lower bound, is equal to f min, and we know that this is lower or equal to our target c. Okay, f max is the maximum value that you can reach of our function. So I know that there exists, let's call this y1 and ab, such that f of y1 is equal to the maximum value of the function, and this is greater or equal to our function value c. Okay, so it's possible that x1 and y1 are two numbers, so it's possible that x1 is lower than y1, or it's also possible that y1 is lower than x1. Okay, so let us assume that x1 is lower or equal to y1. So in the case where y1 is below x1, you can do a very similar thing, except that you have to switch some inequalities. So I will leave this as an exercise for you at home. Okay, so what do? We take the number, let's call this z, which is equal to the midpoint between x1 and y1. Okay, so this is x1 plus y1 divided by 2. And then if f of z is below c, right, if the target of this midpoint, okay, so this is our proposed z, if f of z is below c, we take this to our new lower bound. Okay, then we set x2 to be equal to z and y2 to be equal to y1. Okay, we keep the upper bound and we update the lower bound. If it would happen that this is not true, right, so if of z is bigger than c, then we set y2 to be equal to this midpoint and x2 to be equal to the lower bound that we had before. All right, so we're going to update either the lower bound or we're going to update the upper bound. And then we can do this again. Okay, so take the number z, which is now going to be the midpoint of these updated values, x2 plus y2 over 2. And then if f of z is lower or equal to c, we set x3 to be equal to this number z here, and y2 to be equal, y3 to be equal to y2. If this is not the case, then if c is bigger than c, then we're going to set y3 to be equal to this midpoint here, and x3 to be the same lower bound. Okay, and we continue doing this. Each time we divide, now we're going to divide the interval x3, y3 into 2, and so on and so on. Okay, so in general, at iteration n, we take z to be equal to xn plus yn over 2. So the midpoint between these two numbers. Then if f z is below c, we set xn plus 1 to be equal to z and yn plus 1 to be equal to y. If fz is bigger than c, then we set xn plus 1 to be equal to xn and yn plus 1 to be equal to z, and so on and so on. Okay. Okay, so let's continue here. So by doing this, each time we divide the interval, then we check if the function value at the midpoint is below c or above c, and then we update the lower or upper bound. This gives sequences xn and yn in the interval AB. Okay. So what do we know about these sequences? Well, each time when you update, you're going to update one of the two values to the midpoint of the previous interval. Okay, so in general, if we look at the distance between xn and yn, then we see that this will be equal to 1/2 the distance between xn minus 1 and yn minus 1. Okay, so you update either xn or y into the midpoint of this interval, so the distance will be 1/2 of the old interval. Okay, and xn minus 1, yn minus 1 is 1/2 of xn minus 2, yn minus 2. Okay, and we can continue doing this until we hit the bottom. Okay, so in general we will have 1/2 times 1/2 and so on times 1/2, and then at the end we'll reach here x1 minus y1. Okay, so how many 1/2s do we have? If you go -1 we have 1, if you go -2 we have 2. Here we have to subtract n minus 1 times, so this is n minus 1 times 1/2. So we have 1/2 to the power n minus 1, x1 minus y1. They're both in the interval ab, so this is smaller than b minus a. Okay, which is a non-negative number. So if n goes to infinity, you see that this goes to 0, right? Something smaller than 1 to the power n minus 1. If n goes to infinity, this goes to 0. So what we see that the sequence of numbers yn minus xn minus yn, that this sequence goes to 0. Okay, so xn minus yn is a number. You can put them in a sequence, and the sequence converges to 0. Okay. Good. Now, next, so this is the first thing that you notice. Next, what we notice is that xn is a non-decreasing sequence. Okay, so each time xn is either updated to its previous value, right, and then it's constant, or it's updated to the intermediate value between xn and yn, right? Then xn plus 1 will be the midpoint, so it goes up, but it never goes back to the left, right? So it never goes down. So xn is a non-decreasing sequence, and it's bounded from above by the upper bound of the interval. Okay, and the non-decreasing sequence which is bounded from above, we know that this converges, right? So xn converges to, let's say, some x. Okay, and this x will also be in the interval ab. Okay, we can do a similar thing for the sequence yn is a non-increasing, and yn is of course greater or equal to a, so we know that yn converges to y in ab. Okay, so we had two sequences, xn that converges, yn that converges, and then the distance between these two sequences tend to 0. Okay, so let us show that x and y are actually the same, right? So we have two sequences, both of them converge, but the distance between them goes to 0. So ideally we would have a situation where the limit is the same. Okay, so let's show that x is equal to y. Okay, so how do we do this? Well, let's show that the distance between x and y is actually equal to 0. Okay, so x minus y is equal to x minus xn plus xn minus yn plus yn, and then minus y. Okay, and this is a sum of three numbers, the absolute value, so you can use the triangle inequalities to split it up into three sums: x minus xn plus xn minus yn plus yn minus y. Okay, and now here we see that this here, the first goes to 0 because xn converges to x. This here also goes to 0 as yn converges to y, and this here converges to 0 because of 0.1 that we saw here. Okay, so this is on the left hand side we have a number, and it's less or equal to a sequence of numbers that converges to 0, right? And the number is less or equal to something that goes to 0 if and only if x minus y is equal to 0, okay? If x minus y would be strictly positive, then I can go far enough into the sequence such that I'm actually below the strictly positive number here, which would violate this inequality. Okay, so this shows you that x minus y, the distance is 0, so x is equal to y, and these two sequences converge to the same number. Okay, so we have that xn converges to x and yn converges to y, but y is equal to x. Okay, so both of these sequences converge to the same number. So let's go back to what we actually wanted to show, right? Because we got a little bit lost in the end. So we have this interval here, all these values gets updated, and now we see that all these x's converge to a number, all these y's also converge to a number. What we still need to show is that the function value of this number is exactly the c that we were targeting. Okay, so this is not so difficult, right? So for all n, we know that f of xn is lower or equal to c. Okay, this is just by the construction of our sequences of x's, which had the property that the function value was always below c. And we also know that all the y's have a function value that's greater or equal to c. Okay, and now xn converges to x, so by continuity of the function f, we know that f of xn converges to f of x. Okay, so this uses continuity. Okay, and of course, because every term in the sequence is below c, then at the limit they should also be below c. Yn converges also to x, so f of yn by continuity of f converges to f of x, right? And because every term in the sequence is greater or equal to c, and then in the limit it also has to be greater or equal to c. So we see that f of x is lower or equal to c, and c is lower or equal to f of x. So f of x is equal to c, which is what we needed to demonstrate. So as a consequence of the intermediate value theorem, we will see what's called the mean value theorem as an illustration, let's say. So what do we start with? Well, we start with a function f from some interval ab to the real line, and we assume now that the function f is what we call c1, which means that it's differentiable and the derivative is continuous. Okay, I haven't really defined what differentiability is, and I will not go into detail. I hope you have an idea. So the derivative of a function is the limit for h going to 0 of f x plus h minus f of x divided by h, right? So if this limit exists, then this number that we get here is called the derivative of f at x, and it's denoted by f prime of x. So basically it measures the slope at the function f at the point x. Okay, so C1 states that this exists for every x in the domain AB, and this function here f prime of x is also continuous. Okay, so what does the mean value theorem tell you? Well, it tells you that if this function is C1, then there exists a c in the interval AB. Okay, maybe I should call it x, right? There exists an x in the interval AB such that f prime of x is equal to fb minus f of a divided by b minus a. Okay, so if I draw the picture, we have an interval a, we have an interval b. Okay, so fb minus fa divided by b minus a. Well, if you draw the line from this point here to this point here, right, then the slope of this line, let's call it alpha, will be exactly equal to this number. Okay. So what does it say? This mean value theorem tells you is that there's a point on the function such that the slope of the function at the point is equal to the slope of this line here. So if you take a line piece that's parallel to this line and just touches the function, then for example we see that at this point here, this could be my x, right? Because the slope of this, the tangent line here, the green line, is equal to the slope of this red line here. Okay, so that's the graphical intuition behind the mean value theorem. Okay, so let's prove the mean value theorem. Okay, so f prime is continuous on a compact domain, so we can minimize it. Okay, so we can take the minimum of over the interval AB of x prime, f prime x, and we can take the maximum x in AB of f prime x. Okay, and you know that for any value between these two numbers, I can find something in the domain such that f prime of this number will be equal to this value between these two numbers, right? That's the intermediate value theorem that we have seen a couple of minutes ago. Okay. So what are we going to do? Well, we know that m is lower or equal to f prime of x is lower or equal to big M, right? And this holds for all x in the interval AB, just by definition of the minimum and the maximum. What we can do is we can integrate this all sides over the interval AB. Okay, because this holds for all x, it also holds if we integrate this out. Okay, so I'm going to integrate from a to b of m dx. This is less or equal to ab of f prime x dx, and this is less or equal from a to b of m dx. Okay, this is just a constant number. Okay, so this is m times b minus a, less or equal to, okay, so we integrate out the derivative. Okay, so we know that this is going to be fb minus f of a, and this is less or equal to big M times b minus a. Okay, and now we're going to divide all three of them by the same number, which is b minus a. So we have that m is lower or equal to fb minus f of a divided by b minus a, which is lower or equal to this big number m. Okay, so in particular we have seen that this number here is between the minimum of f prime and the maximum of f prime. Okay, and you know that because of the intermediate value theorem, every number between the minimum and the maximum can be reached by some number between a and b. Okay, so in particular we know that there exists some number x in the interval ab such that f prime of x is equal to the number between these two values, which is now equal to fb minus fa over b minus a. Okay, so this follows from the intermediate value theorem.